In this video, we continue our discussion of asymmetric encryption, specifically looking at RSA. So to encrypt, you have your message, which is M, and you have two variables, which are E and N, which help you determine the C, which is your ciphertext. So the public key is formed using a combination of E and N. To decrypt, you're going to have your ciphertext, and you're going to use the variables D and N to reverse the encryption to get back to your original message. So D forms the private key. So N is a combination of P times Q. Now P and Q are going to be prime factors of N. So think of it this way. If I have two numbers that are prime, 1889 and 3547, and I multiply them together, how hard is that to calculate what N is? It's not hard at all. You could literally just put it into your calculator and figure it out right now. On the other hand, if you are given a number, 6,700,283, and I ask you, what are the two numbers that are prime that make up this number? That would be much more difficult, even though the answer is 1889 and 3547. It's very difficult to break because people have to take complex numbers and get back to the original number. And it's not as easy as this number that we just showed you. In fact, your N turns out to be a number that looks more like this. So identify from this large number what the two prime factors that make up this number. It's very difficult, if not impossible. In fact, that's why computers have a hard time breaking asymmetric encryption, because to compute all the different prime numbers and try to arrive at this number, it becomes nearly impossible. However, with quantum computing on the rise, this could change things. So essentially, the N is going to be your prime 1 times your prime 2, and each of these are 2048 bits. So your N is 4096 bits. So what I want you to do is try to calculate this on your own. So assume that we have M, which is our message, and P is 5, and Q is 11, and then our E is 3. So using the formula that we gave you previously, calculate what the ciphertext would be of this message. You might want to consider using Wolfram Alpha to do your mod calculations. So pause this video and try to figure out what the answer is, and then come back to check your answer. All right, welcome back. Here we are at Wolfram Alpha, where we're going to use it to help us with the mod function. So in order to determine what the ciphertext, we need to use the equation of m raised to the e mod, and then I'm going to do our n. So let's go ahead and plug in the values that would correspond with these. So m is our message, so this is 9, e is 3, and then mod was n, our P times our Q, so 5 times 11. And as you notice here, the answer that it gives us is 14. So after using Wolfram Alpha, given this information, how easy was it to generate the ciphertext? Well, you notice that it was relatively easy because we know what those two prime factors are. But if we were to try to reverse this with complex numbers, it would be very difficult. And in fact, the process is very tedious and difficult to be able to reverse. And so it takes computers an extremely long time to reverse encryption unless they have the key. Thanks for watching my video. Feel free to click the links here to watch the next video of the playlist, continue to the next playlist, or subscribe.